So we're talking about approximate integration. Okay. So we talked last time, we ended by doing a bunch of integrals, right? I gave you a bunch and I said try and try and try again. Well, sometimes when you're doing definite integrals, the try again will fail, okay? So what I'm saying is that sometimes it is impossible to find the exact value of a definite integral. So let's say a to b of some function. So I want to tell you why I'm saying that this is impossible. Okay, so why? Well, for definite integrals, we have the fundamental theorem of calculus, right? So if I want to know how to integrate that definite integral, I just need an antiderivative. Okay, so we need to know an antiderivative of f of x. Okay, I just need to know at least one antiderivative, and this can be really hard. Really hard to do. So I wanted to give you some examples of definite integrals that are impossible really for us to explicitly find the actual value. So the first one is the integral from 0 to 1 ex cubed dx. Okay, you can try all of our integration techniques that we have, substitution, integration by parts, and nothing's going to really work out for you there for that one. Another one, the integral from -1 to 1, the square root of 1 plus x cubed dx. Okay, so there are examples where it's really hard for us to, impossible for us to actually calculate the exact value of these definite integrals. So when we can't explicitly find something, right, instead what we're going to do is approximate that, okay? If I can't know the exact value, maybe I can know an approximate value. So that's the idea here, is that, okay, I can't explicitly find these values, but maybe I can approximate them, okay? So instead, we approximate these definite integrals using Riemann sums. Okay. Do you remember Riemann sums back from Cal 1? Maybe, maybe not. So let me explain the idea for you. So let's say this is my x-axis here, and I want to integrate between a to b some kind of function. So let's say my function just looks like, I don't know, that. Remember that the definite integral corresponds to the area underneath the curve from a to b. So what I really want to find is everything inside of that region between a to b and calculate that area. But it doesn't have a nice shape. If it was a triangle, I know how to calculate the area. If it was a square or a rectangle, I know how to calculate the area, but this is not so nice. So the way we fix it is we cut it up into pieces, this region. and I form rectangles. Okay, out of these regions, so maybe my rectangles look like this. It's not giving me the exact area because I'm missing some little spaces, right? There's little regions underneath this curve where I'm not calculating the area, okay? All right. So I'm going to give you the formula for a Riemann sum. So what you do is you divide the region between A to B into n subintervals of length. We call the length delta x. It's the length of your interval divided by n. Okay, so in the picture, what I did is I cut it up into 4 subintervals because there were 4 pieces, 4 rectangles I had, okay? And then I can now approximate the area under the curve, which is this definite integral from A to B. It's approximately this sum. Sum from I equals 1 to n f of xi star delta x. Okay. So what this formula is saying is that you're adding up all of the areas of those rectangles. The width of each rectangle is delta x, and then the height of each rectangle, it depends on your function. And this xi star, I haven't told you what that is yet. This xi star is any point in the ith subinterval. Xi minus 1 to xi. Okay, so let me real quick go back to our picture up at the top. So all you're doing in each one of these subintervals is you're picking a value inside of them, and that's going to be what you plug into your function to get your height. Okay? So let me remind you of all the ways that you can pick this xi star. There are different methods for picking for choosing xi star. So in the first one, what we're going to do is we're going to look at each subinterval. So let me go up to my picture here for you. And you're going to look at each one of these subintervals here, okay? So I underlined the first one in blue. So one option is you can just take the left endpoint of that interval, okay? So you can just choose, let me scoot up here. You can choose xi star to be the left endpoint of your interval. So xi star would be the left in xi minus 1. Another way you could choose that xi star, instead of choosing the left, what's the opposite of left? Right, so pick the right endpoint, okay? So choose xi star to be the right endpoint. So xi star would be xi, the right endpoint, okay? Those are the two most common ones you probably saw when you did Riemann sums previously, is you saw left endpoint and right endpoint. I've got two more left to tell you about. The third one, so you do have left and right. The third one's going to be in between. You take the midpoint of those two, okay? Choose the midpoint of the interval. So the midpoint, when we use midpoint, sometimes it's replaced by xi bar because you're taking an average. It's 1/2 the sum of the two other endpoints in my, this thing's hard. Xi minus 1 plus xi, okay? And the very last way, which is not very common to see, and you probably haven't seen it before, it's called the trapezoidal rule. The idea is, instead of using rectangles to approximate your area, you're going to use trapezoids, okay? And the way you get the formula, you average the two formulas from 1 and 2. So let me tell you the trapezoidal rule. And we'll do an example of this trapezoid and midpoint rule in just a second, okay? So the trapezoidal rule says my function, it's approximately Tn, which I'm going to tell you is delta x over 2, and I'm just going to give you the formula. F of x naught plus f2 fx1 plus 2 fx2. So all of these have coefficient 2, except for the first one and the last one. Okay. And these xi's, you start at A and you add delta x times I.